lesson, we were dealing in lesson 5, activity 4, with this problem of a 200 microgram sample. And we were wondering when this 200 microgram sample of carbon-14, which has a decay rate of, right here, we can tell what the decay rate is even though it's not given to us. How do I find the decay rate when I'm given something like 0.866? How would I actually find the decay rate? What would I do? 1 subtract what? Okay, 1 subtract 0.866 gives me R, yeah? Yeah, because 1 plus R gives me B. And if I happen to know B, which is what this is, I do 1 minus B equals R, is that right? Is it equal to R or the opposite of R? The opposite. Because this gives me what? 431, right? And that equals, it can't be equal to R, it's got to be the opposite of R, right? Because it's a decrease. Okay, so the decrease here is about 13.4%. We have 200 milligrams, and I asked you to use some type of graphing utility, which you could have just thrown this in your graphing calculator or right into GeoGebra to look at this, to estimate when 25 micrograms of this would be left. So let's just throw this right into GeoGebra for a minute and take a quick peek at it, and then we'll estimate from the graph. I think I already have this done, but might as well put it in. So it was what? F of x equals 200 times 0.866 raised to the x. Oh, what did I type wrong? No 0. Okay, no equal sign. Okay, no 200 either. Equals 200. Did I get it right this time? Yeah. Okay, but you can't see anything because the initial amount is 200, so I have to take my axes and squish them down, right? Come on, turn to a double arrowhead. Come on, help me, help me. There we go. There we go. So you could quickly do this, or if you had a calculator. And so we can take this little snippet here. I don't have snippet on here, I guess. You could just snip that and put it in. So the question is, when will it be at 25 micrograms? Okay, 25 micrograms is on the y-axis, and so 25 would be roughly right here. So you would draw, let's put it in with GeoGebra. GeoGebra can do it exactly. Y equals 25, there you go. And now you want to see, where does y equals 25 intersect with the green graph, right? Where do they intersect? The green graph is called G. Excuse me, the black line is called G, and the green graph is this function. So let's intersect them. And so we've got G with, I'm surprised they didn't give f of x an object name. That's interesting. F of x. There's the point, and there's the coordinate. So it will be 25 micrograms, about 14.45 years. Now, you're probably not going to get 14.45 when you're just looking at a graph and estimating, but anything in the ballpark of 14 years is what we were looking for there. Okay. So this is all we have available to us right now. If we have a problem that we're trying, that's exponential, and we're trying to solve for the variable that is now an exponent or a power, because we haven't learned, well, we haven't reviewed yet how to undo an exponential. Okay, so this is the only resource we have right now, is to use a graph to estimate. So this question can be translated into this equation. If I had 200 micrograms that was decaying at this rate, I want to know, I want to solve for t, how long will it take for it to reach 25 micrograms? So we can't undo exponential equations right now, but we will in just a few minutes. So we have to Rob, why don't you finish this off for me in your lovely voice, the function. Rob M. I want you to, that's why I picked on you. Yeah, so come on, give it to me. Oh, you're not? Oh, come on. Come on. Yeah. That's a solid no. You don't like to sing? Oh, I picked the wrong person, huh? All right. So you know the song, do you? All you need is love, love. All right. All you need is logs. Logs will undo this. Okay. It performs the same function that adding and subtraction do to each other, multiplication and division. Exponentiation and logs undo each other. They are inverse functions of each other. And again, the fact that we know this graph that we just looked at is 1 to 1. If I draw a horizontal line throughout this at any point, it's 1 to 1. Now notice your end behavior here for this graph. As time goes to infinity, this approaches 0. The limit is 0, but it would never be 0. Okay, so there's always going to be some trace amount. And similarly, it said, you know, when you look at drug dosing, that a similar thing is true. Okay, so a logarithmic function that has base b is written this way: log base b of x. This is your input into your log function. This little term right here is called the argument. Okay, so sometimes I might say, what's the argument? It's just the input. It's the inverse function of the exponential function that has exactly the same base, b to the x. Okay, it's just an artifact of the variables here. Well, I won't say that. All right, so here we go. So here's the equivalency between them. This statement, b to the x equals y, is the same thing, equivalent. That means they're exactly the same equation as log of the same base. Notice the output for exponentiation becomes the input for the inverse. The answer for my log is the exponent. So logs are just exponents. Okay. So this is the statement that helps us go between an exponential problem to a log and vice versa. Right. So this should be a review for everybody, I hope, since we just ended 107 with all this information. All right, so we know that common bases, some special bases we work with is the common log, that when we see log of x, we understand that to be log base 10. It's never written in, it's just log x means log base 10. So if you wanted the equivalent exponential problem for log x, same base 10, the input to my log is the output for my exponentiation. So y is the exponent here in this particular case. Log base e has to do with continuous growth. E is used for any type of continuous growth or decay. That's natural log. Okay, natural log. All right, well, continuous growth. Sorry about that. That's pretty much what we're dealing with. All right, so I'm going to do these first couple in a little different way. I just want to kind of reinforce the idea of functions from a point on one function switches the coordinates to get the point on its inverse. So if I was looking at 3 squared equals 9, my input here is 2, and my output is 9. What's going to be the corresponding point on my inverse function? 9, 2. They just switch spots. Okay. So when I go to write my log now, my input is the answer to my exponent. So I write log, exactly the same base. My input or my argument is 9, and my answer is 2, because my answer is the original exponent. 3 squared equals 9. Log base 3 of 9 equals 2 are exactly the same statement. Okay, let's take a look at 10 to the negative 4 equals 1 over 10,000, which is the same as this. Is that correct? 1 over 10,000 is 0.0001. Agreement on that? I just rather write it as a decimal. Okay, so what would be the input here for this one? Jenna, what would be the input for the exponent? Oh no, not the not to rewrite it. What? Just looking at this, what's the input? What's the output? Yeah, and what's the output? Peter? Okay. So now when I go to look at my log function, what's going to be the input? Jackson? Yeah, here's the input and the output for my exponential function. What's going to be my input and output for my log function? Right. So now when I create my log function, I say log. I don't have to put base 10 down there. My input to my log is the output from my exponential. So 0.0001. My answer is the exponent, negative 4. So this one, look at this. We know the square root of e is e to the 1/2. We have a special base. So the natural log of e to the 1/2 is 1/2. You just lift off the exponent. When your bases are the same, your base here is e, you have e to the 1/2, your answer is 1/2. They undo each other because they're inverses. All right. Now we're going to go the other way. So we have log base 6, so our exponential equivalent equation here would have what as my base? What would be my base here? Be my base for my exponential equation? 6. My answer to the log is 2. A log is just an exponent. And there's my answer to that one. 6 squared is 36. Next one. Base 3. The answer to my log is my exponent. 3 to the 0 is 1. Everything is good. So 3 to this power equals 6 to this power equals. So what would be my next one? Can someone help me with that, Maddie? You can pass if you don't feel comfortable. Yeah. Yeah. Yep. Thank you. Any questions on that one? 10 to the negative 3 is 1,000th. And finally, you see a natural log with base that has base e composed with its e to the 5th. They undo each other. So this just simply becomes e to the 5th is e to the 5th. That's what that says. It's kind of like a trivial statement. You just lift off when your base of your log and the base of your input are exactly the same. They undo each other, and you just lift off that exponent. Because of the next property. This works this way because of our inverse properties. It's easier to look at this first one than this one. So let's start with this. You have this function b to the x. You compose it. Let's think of that as our inside function, like g of x. And then f of x would be log base b of an input. When you compose inverse functions, you come right back to where you started. So this first statement would be if I had these following. Let's suppose I say f of x equals b to the x. And let's say g of x is log base b of some input x. So if I compose them like this, oops, that's the next one. Like this. Okay, so I take f of x, which is b to the x, and I put it in right here. I come back to my original input, which is x. Because this says b to what power is b to the x? B to what power is b to the x? What power has to be the x? You just lift off the exponent. These two undo each other, just like adding and subtracting. So that's where your exponential function is the input into your log function. Now we're reversing that because we know that one thing is always true about inverse functions and only for inverse functions. Inverse functions are the only two functions that you can compose, change the order of the composition, and come right back to where you started. So now, what about putting this function, the log function, up here into my exponent? That's what looks like this. B raised to the log base b of x. They undo each other, and you come right back to x. So to give you an example of that, it's harder to say than it is to see. So let's suppose I did this. So this is asking me 10 raised to this power is what? Well, what does this represent? Log of 100. What goes there? Log of 100. 2. 10 to the second is 100. So my answer to this is 100. These just undo each other. They're inverses. This says, what power do I raise 10 to get 100? My answer is, excuse me. This says, what power do I raise 10 to get 100? The answer is 2. And then you raise 10 to that power. You come right back to where you start. Okay, so this thing just represents the number 2. Then you raise 10 to that power, and you come right back to 100. Logs and exponents undo each other. See, and you got your exponent and your log, same base. They undo each other, and you get x. Logs are exponents, yes. All right. So you don't need any calculators here. You look at these. This first one, most people, going in this order, most people get it. You just lift off the exponent when your bases are the same. It's the other one that messes with your mind a little bit. So this is just 8.4 because you have two inverse functions here, log base 10 and 10 to a power. So your answer is just your exponent. Now you got 10 raised to its inverse function, log base 10. These undo each other, and your answer is 2.7, just like these undid each other. So you just have to recognize these things. You can do them, out, but it's much easier just to recognize when you're putting a log function and an exponential function together. And you can just create your own in practice. I know I'm being silly, but you could just do a couple of those. All right. Now, the two exponent properties that we're going to be using the most for our application problems is the power to a power, or your exponent property right here. Remember, log is a power, log base b of a, all by itself. That's a power, or an exponent. And now we're taking that exponent and we're raising it to another exponent, a power to a power. When we have that with our exponent properties, we multiply our two powers. So when you have a log of an exponential like this, the r just comes down in front and multiplies the remaining log. The other thing that we often need to do, because we don't just work with logs, common logs and natural logs, is if we get a log of another base, we have to be able to put this into our calculator to get an estimate if we want an estimate for our answer. So if you have, say, log, let's work on this one right here, log base 3 of 25. The first thing I want to do is to use this first property and rewrite 25 as 5 to the second power. So that's using this first property. So I've taken care of the first properties done right here. I rewrote 25 as 5 to a power. Now that 2 is going to come down in front and multiply the remaining power, which is log base 3 of 5. Now this is the exact answer. If this was part of a problem, this would be the exact answer right there. However, sometimes we'll want to have an approximation. So to get the approximation, the only choices I have on my calculator is a common log button and a natural log button. So I have to convert this with this change of base formula. I can use either the common log or the natural log. It doesn't matter. So you take the natural log of 5 and divide it by the natural log of the base, or you could do the common log of 5 divided by the common log of 3. Okay, they're both exactly the same. So let's take a look at that. So what are we going to do? We're going to do 2 times the common log of 5 divided by the common log of 3. And that's about, as an approximation, 2.9. What was it, 2? Because this keeps falling off my screen for some reason. Okay, so let's say 2.93. All right. Okay, well, I'm just going to demonstrate this. Thank you. And 2 times the natural log of 5 divided by the natural log of 3. Exact same answer. Okay, so it doesn't matter which one you do. Now, your fellow students said we can change the base by going to math. And we're down here. Okay. Slow down, Linda, slow down. You have an 84? Yeah, this is an 83 plus. Okay. So when it comes to test, graphing calculator, most of the, no, those have logs on them. Right, I don't think that this has. No, you have to use this, right? Sometimes I'm going to want exact answers and sometimes I want estimates. So yeah, you'll just use that. That's why we have change of base. So we can use any of these, less expensive calculators. Oh, I forgot to tell you. If you have a smartphone, one of my students showed me today, they can get the TI 83 Plus right on their phone as an app free. Yeah. He had it out in class. I was like, whoa. So anyway, he's now got a graphing calculator. It was great. So if you have a phone that has that capability, you might as well take a look at that outside of class. All right. So now we have enough knowledge to actually, let's solve the problem we started off with algebraically. So let's see, we had 25 equals 200 times 0.866, I believe, to the t power, right? That's what we started off with? Okay. Just going to go down an inch or so here. I got to take off my boots. All right. So you want to solve for t. So the first thing you want to do is to get the expression that the base with the power all by itself. You want to isolate that. Get that all by itself on one side of the equation. So the first thing we're going to do is divide both sides of this equation by 200. 25 over 200 I can reduce quite easily. It's 1/8 equals 0.866 to the t. Okay. I want to undo the exponentiation. To undo it, I have to take the log of both sides. It doesn't matter whether I take the common log or the natural log. It's really up to you. I tend to use the natural log. I don't know why. I just happen to use the natural log. So I'm going to take the natural log of both sides. So I'm going to scoot in a natural log on both sides. The natural log of 1/8. Think of it. Think of your graphs for logs. All right. So your logs between 0 at 1, you're 0. So any number between 0 and 1 is going to be a negative power. Okay. So here's natural log of x. So this will be a negative power. You're going to end up dividing both sides by natural log of 0.866. That's a number between 0 and 1. You'll have a negative divided by a negative, which will give you a positive value there. So just making sure like you can at least get some kind of estimate for what you're doing. So you use your first property we talked about, the exponent property that we talked about just a minute ago here. The t is going to come down in front, and it's going to multiply the natural log of 0.866. This is just a constant. It's just a number. It's the coefficient of t. The natural log of 1/8 is just a number, a constant. So this looks just like the equation 10t equals 2. That's how simple that equation is. All that other symbology in there is just messing with your mind. So you just got to create a visual field that makes that look as simple as 10t equals 2 to yourself. So you want to solve for t, which means you've got to divide both sides by the coefficient, which is the natural log of 0.866 on both sides. And as you do these over and over again, folks, you're going to see that your denominator is always either the common log or the natural log of whatever your base is. It's always going to end up there when you have equations like this. And what's this number always going to be? The numerator, the natural log of what? Whatever this number is here divided by your original amount. They're all done the same way. All right, so let's find t by putting this into our calculator. So again, you could do common log or natural log. So we have the natural log of 1/8, which is the same as 0.125. And I'm going to divide that by the natural log of 0.866. And I get approximately 14.45 years. That's what we got from the graph too, wasn't it, when we did the GeoGebra graph? I believe that was exactly the same answer right here, 14.45. Okay. So t, and now you want to say is approximately 14.45. Because this is the exact answer right here. If I said, give me the exact answer, you would just leave it like this. If I say, give me an approximation, then you would, and I'll tell you 1 or 2 decimal places round. Okay. All right, so that's it for today. The rest of the time you have on your activities. There's lots of activities. Let's see. Yep, lots of activities. I gave you lots of activities today, and then more practice. You may want to wait for the big baby until later, but if you want to work on the big baby, it's a fun problem. Okay. The big baby problem. Any requests for music? I know, but that was from my first class, so what am I going to do? Say I don't like your music? Yeah. No, I'm not going to say that. Any requests? Red Hot Chili Peppers, okay. Oh, good. Where is it? $21.07? I don't even have my, let me. Down, I don't even see it. Where are we? Oh, yeah, from 2107. Okay, yeah, 2017. Thank you. All right, I can go right on my Dropbox and fix that right now. Yay. Do I have my Dropbox on here? I guess I don't. Oh. Oops. I was recording all that, by the way. It